Can engineers build their own camera-enabled embedded systems? I'm your host, Todd Baker, and in this episode of The Current, our very own intelligent sensing engineer, Gunn, takes us through new solutions he's developed to make these proof of concepts for machine vision easier. So we've talked a lot on this podcast about how embedded design is changing a lot. It has changed a ton over the course of the last 10 years and even the last 5 years and 2 years to where, systems now need to be a lot more interactive with the environment around them. And the designs that we used to do as engineers, where we had a couple of sensors that are detecting temperature, detecting light, detecting motion, and we had a couple SPI ports, a few I2Cs. We could feed that into a microcontroller, collect that data. Maybe there's a user at the terminal, and we just want to operate on base the button pushes that user's doing. And now we want embedded systems that, instead of being kind of controlled by the user that's present, we want systems that are actually able to detect exactly what's going on in the environment around them, in some cases see the environment around them, and make decisions without a user even being there. And that's a really exciting direction for technology, but it can also be a little bit daunting for embedded engineers who are more used to working in that microcontroller type of design, because now we see very sophisticated imaging sensors with high-speed data interfaces that need a processor to be able to handle that, to be able to run the application and the complex applications that are required in those systems. And so now we've moved from maybe a system where we had just a bare metal microcontroller to a full-blown Linux operating system with multiple threads, a lot of complex algorithms going on in order to interpret what's going on in our environment and make decisions right then and there that the system are going to take on. So today, I'm talking with one of our experts in this arena, Gunn, who's a multimedia processor specialist on Future's Intelligent Solutions team. And we're talking a little bit about the things that embedded engineers have to consider in these systems, and also a little bit about a few of the tools that he and FIS have developed that are going to make those designs a little bit easier for customer engineers to bring up to speed. So Don, how you doing today?
I'm doing well, thanks. How are you, Todd?
Great. Thanks very much for joining me. Definitely appreciate it, and always great talking to you. So talk to me a little bit about some of the challenges that you've seen when you're working with customer engineers that are working on these kinds of systems. What are some of the things that they have problems with? What are some of the gotchas as they're developing those systems with an imaging sensor and a processor?
Well, one of the challenges with integrating an image sensor into a new system is trying to prototype and do some sort of proof of concept type of work. With various image sensors, they either come as a raw sensor or as a camera module, and then you need to find a way of connecting that up to your embedded system or your evaluation kit from a processor manufacturer. So that's probably the biggest challenge. The modules, if you can get a module with the sensor that you're looking for, they have different types of connectors on them, and those are not necessarily something that you can just plug into an eval board.
Right. And so you end up in a situation, I guess, as an engineer where you either have to create your own hardware first, or you've got to figure out some way to interface those devices, which is kind of a tall order when you're just initially doing a design and you don't want to have to do a full-on board spin.
Exactly. So right now, the way it is if you have an image sensor and you have an eval board, you essentially have to develop an adapter board to bridge that connection there, because these sensors are typically MIPI interfaces, which is a high-speed serial interface. Signal integrity is a challenge. So you can't just use jumper wires to connect up an image sensor to an eval board. So you would have to develop a specialized adapter board to connect the two.
Absolutely, and that adds a whole new level of complexity and time to finish the design, which nobody wants to deal with. We need to get things done, and we need to get them done quickly. So any tricks or tools that you've seen engineers use kind of as a best practice to kind of get over that hurdle and get to a point where they don't have to actually spin their own board to bridge the camera and the processor eval?
Well, I think primarily right now, you have to do your proof of concept with a sensor that is different than the one that you're using or that you intend to use. Unless you're planning on using the one that is provided by the manufacturer that's specifically designed for the eval kit. So that sort of presents a challenge. You don't necessarily know exactly what you're going to get in your finished product when you get your imager hooked up. So it's not an ideal situation to be just using the sensor that's available instead of the one that you want to actually use.
And so, have you guys worked on develop anything for customers that can help to bridge that gap? Any adapters or anything like that?
Yeah, so right now we actually have a number of image sensor modules available based on primarily on onsemi image sensors, and they actually have all got a common connector on them. So what we've done is we've developed a little adapter board that we're calling it Cyclops that will let you plug in these onsemi modules onto the adapter board has two separate connectors on it. The first one is the mini SAS connector, which is the standard connector that NXP puts on all of their latest eval kits for hooking up a MIPI camera. The other one is a Raspberry Pi style ribbon connector, and you can use either one to connect these sensors to an eval board.
Okay. Okay. All right. So that sounds like that takes a lot of headaches out of the design process for a lot of engineers. So we've developed this for, fairly common MIPI interface coming out of a lot of the different camera sensors, particularly on Semi's Aptina family. What about on the processor side? I mean, what processors is this ready to connect to, and where are we kind of, able to help customers on that side?
So there's a lot of manufacturers out there that are making processors with image sensors. So we have NXP, ST, Renesas. They all have products with MIPI camera inputs. Essentially, what you can use this with is any board that has a processor that has a MIPI camera input, and either a mini SAS connector or a Raspberry Pi style ribbon connector on it, and you can connect the sensor, any of these sensors, right up to these eval boards.
Okay. So does it end up being just as simple as taking this kind of bridge card, plugging in your imaging sensor on one side, plugging in the processor dev board on the other side, and you're good to go?
Yes and no. Depends on the image sensor. So with embedded systems, you have a kind of a customized Linux kernel and the drivers that go with that. Some drivers are available at open source, like the camera, for example, the OV5640 is a very common image sensor, but it's actually being discontinued, so a lot of customers can't use that anymore. But that was well supported in the open source community. But a lot of the sensors that you may be interested in don't necessarily have a pre-canned driver that you can just grab and go, and you can't just plug it in. So what you have to do is you have to either create a custom driver or obtain a driver for the sensor that you're using, and then you have to integrate that into the Linux kernel, and then sort of customize a few things at a low level in the device tree for your system. So you'd have to add in support for the hardware that you're adding, and then driver support on the software side so that you can actually bring up your image sensor and test it out.
And where typically would an embedded engineer find the, if you're looking for those drivers and you need to find them, where are the best places to go look for that if you've got a new camera module and you're starting a new project?
That's a good question. So in a lot of cases, they just don't exist. So one thing that we've done with the sensor modules that we support and that we provide for customers is say specifically for the AR1044 or AR0144. We've actually obtained compiled some code that was provided by onsemi and then modified that and adapted it to be able to run on NXP eval boards, for example. So that's, but in general, you may not necessarily be able to just get a driver provided. So that would, oftentimes that would actually involve customers developing their own driver code specific for the sensor that they're using.
Right, definitely a time-consuming thing on that. So, I think that it's always one of the things that I love about working with you guys on the FIS team is you guys can help customers get that done quickly, find where those drivers might exist, either on the processor side or with the camera module manufacturer, and kind of expedite that. Because if you end up in a situation where you've picked a module and maybe you've picked the camera sensor that doesn't have a readily available driver, the amount of time that can add to a project becomes excessive.
Absolutely,
definitely a painful thing.
Yeah. So in the case of this system that we have right now, if a customer wants to evaluate the AR0144, that work has been done, and it's more of the driver code is provided as a proof of concept, so you can get a video stream going up. In this case, it's a raw image sensor. There's no ISP involved, so you would have Bayer data coming in, and then you can do what you want with that video data, whether you want to stream it to a display or
Right.
compress it and send it out over Ethernet. But in that case, we can actually help customers. I'm the one that went through building all that up and integrating it into the image. So if anybody is out there interested in testing out that sensor, then I can work with them to get them through that. The first time I did it I'd never done an image sensor before integration. Spent a couple of months tinkering around and getting things working. When I did it the second time on a separate eval board, it took me about a day. Once you've been through all the bumps and hurdles, things go a lot smoother.
Right, like riding a bike.
And
once you've done it once,
yeah,
you gotta get it down.
Yeah, absolutely. And then we can help people through those hurdles and get them up and running with kind of a basic video stream, and then they can take it from there.
Awesome. That's powerful. I mean, I think, when you've got, engineers that are trying to figure out things for the first time, having an expert sitting alongside you, helping to expedite that is just huge. So you mentioned that with this particular sensor, it's, you're getting a raw image output directly from this particular onsemi Aptina sensor going into the processor. Now, what about if the sensors out there that might have an ISP, an image signal processor already on board that's doing some of that? Is there anything different that needs to be done there? Is it required to have an ISP to use this bridge board or this adapter board, or is that something that doesn't really matter depending on the sensor?
Yeah, so it's not required. You don't have to have an ISP, but in this example right now, if I want to stream the video from a raw sensor to the display, I have to do a Bayer conversion. So that's taking raw Bayer data from the image sensor, and that has to be converted to RGB before it can be displayed. So the sensor itself can stream at 60 frames per second, but when you're doing that Bayer conversion in software, the actual reality of what I'm getting on my screen is about 5 frames per second, because there's a lot of overhead with doing that video processing. So that overhead can be eliminated either if your specific situation, you like say for machine vision applications, if you don't need RGB data and you can work with the raw data, you don't need to do that conversion, and you can just work with the raw data as is. If not, if you do need that conversion, you can either have an ISP external, so it would be between the image sensor and the main processor, or we're actually starting to see a couple of manufacturers out there that are starting to integrate ISPs into their processors, so that actually will handle all of that functionality and offload the main processor. So right now the Renesas and NXP both have processors with this functionality. And that's something that can be integrated into the whole system to improve performance and improve the quality of the video coming out of the sensor.
I think we're probably going to see that continue to increase a lot, as there's a lot more machine learning applications out there, object recognition applications out there, like we're talking about today. I think those ISPs are going to become as important in the processor and the multimedia processor area as so many other peripherals we've gotten used to there.
Yeah, that's actually a very good point. An interesting feature of these processors that have the ISPs built in is both the Renesas and the NXP options have a built-in machine learning hardware acceleration, so you can very quickly process video data and actually extract the machine learning information that you're interested in. So if you were trying to do that without an ISP and without that machine learning accelerator, you have the overhead of trying to convert your video data in software, and then you're trying to run the AI inferencing also in software, so your performance would drop significantly. If you're using a device that has a built-in ISP and you have a built-in machine learning accelerator, you'd be going from probably 2 or 3 frames per second, say for example if you're doing object detection, up to probably 40 or 50 frames per second to do the same thing.
That's a huge improvement. So I mean, just that small piece of hardware is going to make a big difference for anyone that's designing with that kind of a system. So that's beautiful.
Absolutely.
So you mentioned you've done this, a couple of different designs with this now, and have started to get very adept on the image sensor to processor interface. Have you got an example of kind of using the Cyclops adapter board in a system and how that works?
Yeah, I do. So maybe what I'll do first is I can show you what the actual the adapter board looks like. So let me just unplug it here. So this is the Cyclops board that we've developed. So you'll see there's the image sensor module right here, and it's on kind of a little ribbon connector, and then ribbon cable, and there's a connector there. On the front of the board here, this is the ribbon cable connector if you have like the Raspberry Pi style MIPI interface on your board. And then on the back, we have this mini SAS connector that is used on the majority of the NXP eval kits. So what I can do is I can now I can just plug this in to the cable that came with my eval kit from NXP on the 8M Mini.
Right.
And plug that in, and then I will plug it into the board. And I will share my screen here. Okay, so on the right, that's just a serial console for the board, and in the background, that's the main output of the eval board. So we'll just boot up here. Okay, so that's the Wayland desktop in the background there, and then my serial console. I can log into Linux, and then from there I can just set up a simple GStreamer pipe to get the video from the AR0144 onto the main display of the kit. So GStreamer, and then we'll have V4L2 source. So that's the video for Linux subsystem. So that's the driver that I've sort of put together is supporting that subsystem. And then we have to do the Bayer conversion. So we do Bayer to RGB, and then we want to send it out to the Wayland display. So we'll say Wayland sync, and then sync false. So we'll hit that, and there we go. So you can see that's the initialization code there that I've just added in for debugging purposes. You can see all the registers that are being written to the image sensor. And then in the background, you can see the video coming from the sensor. In this case, it's a monochrome sensor, and it's a global shutter monochrome sensor. And we're getting about 5 frames per second here right now because of the Bayer to RGB conversion being done in software. So I can hit Control C on there, and it shows me exactly what my frame rate was. So it showed 141 frames at 5.3 frames per second.
Okay. So if we're wanting to do some kind of object recognition, if we need more than 5 frames per second, what are our options? I mean, how do we get to a point where we can, handle more frames? Is that just a matter of putting in an ISP, or what all is required there?
Yeah, so machine learning is a processing intensive application. So having a machine learning accelerator built into an embedded system is pretty key in performance. So we've discussed this and what it would look like. So I could just show you a little quick demo here. I will show you what that looks like. So I'll show the screen. And over here I have the MX 8M Plus. You can kind of see that from the prompt here in Linux. And what I'll do is I will run an object detection using a video stream that does not require an ISP in this case. So this is RGB data coming into the part. And this is the PyIQ demo framework is something that you can install on any of the MX8 eval boards from NXP and run these demos. So you can see in the background there, that's live video as we're sitting here, and it's identifying the different things that are in my room here. It's identified me as a person, the chair that I'm sitting in, and you can see up in the corner here, depending on what's happening in the scene, we're getting 35 to 45 frames per second in the inference. You can also do to see the difference that that you get with the machine learning accelerator or without. I can show you. I've got a switch video that I can switch back and forth between CPU inference and NPU inference. The NPU is the hardware accelerator in the 8M Plus that accelerates the AI learning. This particular demo is set up with a just a pre-recorded video. So we're seeing the inference time here is about 16, 17 milliseconds, and that's running on the NPU, which is the accelerator. If I switch to CPU, you can see here that that's gone up to 150 to 200 milliseconds for the same function. So this would be what you would get on a part that doesn't have that acceleration block. And then if you do have that accelerator in here, this is the performance that you get. So it's a pretty substantial difference when you're using a part with and without a machine learning accelerator.
Excellent. No, I mean, a huge difference, and just a great demonstration to show how that extra piece of hardware built into the processor can make an enormous impact on an application, particularly when we're talking about machine learning and a system that's able to really adapt to the environment, understand the environment, react to the environment very, very quickly. That's exciting.
In this for this particular processor, having an ISP on the board would actually probably get you up to about 10 or 12 frames per second if you're doing an object detection. But if you want to go faster than that, then a part like the MX 8M Plus from NXP or the RZ V2M from Renesas with built-in machine learning acceleration, that'll get you up to the 40 plus frames per second for probably a 720p video stream doing object detection, and you can detect people going by, you can detect chairs, backpacks. There's a large number of things, and you can specifically train your model for whatever it is that you're actually looking for.
Okay. And then, so for that training, I mean, are those libraries already in existence? Is that something where we in the FIS team can help with that training process? How exactly would that work for a customer that wanted to, maybe they don't want to detect chairs or backpacks, maybe they want to detect apples, something like that. How would we go about that, helping that customer?
Yeah, absolutely. So we have some experience with doing transfer learning and customizing models. And that's actually, we can sit down with customers and help them work through it if they've never done it before, or we can provide like lab type material so that they can kind of work through it themselves and then perform their testing and modifications as required on their own, and then have the FIS team here to support them in that effort.
Excellent. Well, this is great, Don. I think what we've got here really is going to be very helpful to any embedded engineer looking at this kind of design. Again, getting whatever camera interface that they're looking at, or camera module or camera sensor itself interface to an eval board or dev board of their specification is huge, and makes the design go a lot faster, and definitely excited about what we can do there. So really appreciate your time, really appreciate you showing this to us. For anyone that's interested in this kind of a design or application, Future Electronics Advanced Engineering Group and our FIS team and Don himself, we're happy to help out. We'd love to meet with you. We'd love to have a conversation with you, understand more about your design and how we can assist, get you to production faster, get you to production, with a better solution, with a lower cost solution, and get you successful in your end product. If you have any questions at all, please reach out to us at Future Electronics. Shaping the Future at futureelectronics.com. Again, that's Shaping the Future at futureelectronics.com, and we look forward to helping you out. Don, thanks again so much for the time and for the demonstration. We look forward to getting these Cyclops boards into the customer's hands and helping a lot of people with their designs.
All right, thanks, Todd. Thanks for the interest in the Cyclops board and the work that we've done to help customers get to market.
Absolutely.